during the talk you have any questions, please let me know. We can stop there and finish that question. That would be helpful for us. And I am expecting this session to be a bit interactive so that you don't get bored easily. This might get a bit heavy when I try to explain the neural network part, but please stick around. At the end of it, I hope that you will also enjoy neural networks and artificial intelligence as much as me. What I am planning to do is, for explaining AI, I am taking digital twins as a premise. Digital twins for predictive maintenance. Now, if you have, I think most of us have heard the word digital twin. If you, there is a lot of hype around it, and yeah, in especially mechanical domains, everyone wants a digital twin. Every factory wants a digital twin. When we hear this word digital twin, this kind of fancy image comes in mind, right? Some 3D infographic with lots of moving parts and connectivity and high-end simulations and so on. Well, yes, digital twin is that. A pure 100% accurate digital twin would be that. A digital twin is essentially a virtual replica of a physical object, system, or a process. This is your Wikipedia definition that everyone knows. But can be used to build a digital twin model itself. When you see a digital twin, there are three elements for a digital twin. You need a real world entity, you need its virtual representation, and then a connectivity between the two. So for example, if you would build a digital twin of a propulsion system in an aircraft, you would need some sort of data connectivity between the two. That is what everyone expects, and in academia that is not really possible. You cannot possibly have real world connectivity to the data. What you will have is static data, right? You can get open source data from journals, from internet. You can get static data while collaborating with industries that they can share with maybe in a CSV or an Excel file and so on. So what we want to do is build a digital twin with that, with the text data, not having connectivity to a real world system. That may help the context here. So I believe this is also something that many people already know, but I just want to cover all bases here. Digital twins can be at various hierarchies. You start with a component twin. It can be a very small part of your entire system. Like in a battery pack, a single lithium-ion battery cells process can be created as a component twin. That would also be digital twin. It would show the charging and discharging cycle, how the ions move from each terminal, how the battery cell degrades over time with the accumulation and so on. The second would be an asset twin. Now, an asset twin would be having multiple components. So, for example, a compressor, right? So, it would have multiple components that are attached and they are moving in sync. So, you can build a twin with respect to an asset. This is what digital twins also serve functional purposes. This is one slide that I have worked on and what we have defined over the last couple of years. But moving forward, there may be other functional areas where digital twins are required. So this is with respect to predictive maintenance especially. We have a diagnostic twin, a performance twin, and a what-if analysis. So how do we segregate them? A performance twin would monitor performance-related KPIs. So something like an efficiency would come under the purview of performance twin. A diagnostic twin would forward all all these approaches, all these functional digital twins can be achieved with various modeling approaches. So traditionally, everyone has used physics-based modeling techniques. So traditionally, as I was saying, people have built digital twins using physics-based techniques. These are mathematical equations that are derived from your actual physical laws, laws of physics. So, for example, you want to simulate the airflow over a jet using the Navier-Stokes equation, and then solve that Navier-Stokes equation. Very long, they are computationally expensive, and it's almost impossible to scale them. So, for example, if you take I would go to one of our, take a grid of some, let's say, 32 by 32, and then on each of these blocks you will solve this physical equation, right? So you will have a long PD, and you will use, as I was saying, for example, the Fourier implicit method to solve this. Now 32 by 32 is a very small grid space. If you have worked on modeling, you know that you would want a 3D grid, and on top of that you would want that to be at least in a few thousands and so on. To solve such kinds of